One of the more recent problems on the AP exam was determine the resistivity of a material given the resistance, length, and area of area data in a table. So you look at the table here, and there were some numbers here, and they said, how could you graph and determine the resistivity? And they gave you extra columns, and they said you could calculate things, and the logical thing to do would be to calculate L over A, would be the easiest thing to do, because if you look at the formula, Y equals Kx, and you look at resistance as the Y variable, and L over A is the X variable, the slope of the line, when you plot it out on a graph, should be the resistivity. So that slope winds up being the resistivity. So, additionally, if you look at this, we talked about how the area wants to flow from a high potential to a low potential. That will be the case all of the time. That's true in all of physics. It's a big idea that runs throughout physics, that things want to come to an equilibrium. A pendulum swings back to the low point, goes back up to the high point, swings back to the low point. It wants to go from the high potential to the low potential. A few things that we want to kind of go over, just some things to understand, is grounding. The reason a bird doesn't get shocked up on the high wires is because he's not grounded. He's not touching the ground, and so there's no path through him to the ground. But if a person touches that high wire, there is a path to the ground. And if you look at the picture on that diagram, the battery, below the battery is this ground. That's just the symbol for ground. The long and shorts of the battery, and the resistance is right here. But the wires, the person's touching it, so he's also touching the ground, and so since that circuit is tied into the ground to keep it grounded, there's a path through the person or a path through the circuit, so the electrons will flow through the person and through the wire, and the person gets shocked. Talking about closed and open circuits. If you look at the diagram to the right, there is two circuits, one where the knife blade switch is closed and one where the knife blade switch is open, and they're hooked up to a battery and a bulb, and when it's closed it's on, and when it's open it's off. It's kind of like the switch that you turn in the classroom when you walk in. Short circuit bypasses the circuit and heats up quickly. The reason, because electrons are smart, they take the path of least resistance. So rather than go through the light bulb, which has high resistance, they're going to flow through that wire that's been established, that's shorting out the bulb, and it's going to heat up very quickly, and the battery's going to drain and heat, and potentially there could be a fire if it was a high enough voltage. So what do we do about short circuits? Well, we want to prevent them. So if there was a short circuit in the next circuit, say over here, and the switch were closed, things would start flowing very, very fast around the circuit, bypassing the bulb or whatever it is there that it's running. So you insert a fuse into the circuit, and that fuse will burn out and protect and will stop the flow of electricity at that point and protect the circuit, and then you go put the fuse back in. And at your house, there's breakers now. In the old days, there used to be fuses that would burn out, and people would put a penny in there, and they would overheat and it burn houses down, and so that wasn't a very good idea, and so they came up with breakers now for houses. Now, if you can't remember this formula, I believe that what you're going to have to do is quit physics. Get the pun, quit, Q-U-I-T. The formula is really Q equals I-T. And Q is charge. It's measured in coulombs. It's a coulomb is an amp second. Or if you think about it, I like to think about it this way, an amp is a coulomb per second. It's how many little electrons or Coulomb's just a bunch of electrons that are flowing past a cross-section of the wire in a given second. And so the formula is current is charge over time, and if you rearrange it, you get the formula there in red that's on your formula card. Now, one of the things you want to memorize, because it's going to come up over and over and over and over and over again as we do calculations throughout the many chapters in electricity, is the elementary charge, which is the charge on the electron, which is 1.6 times 10 to the negative 19th coulombs. That's the magnitude of the charge. Now, we know that the electron is a negative 1.6 and the proton is a positive 1.6 times 10 to the negative 19th coulombs. So that's the absolute value of the elementary charge on the electron. Elementary charge being the proton or the electron being negatively charged. Energy conversions. Many energy conversions can take place. We've talked about energy conversions in the past, changing potential to kinetic. Electrical energy can also be converted into things like heat, light, sound, potential energy, and kinetic energy. So we can set these, if there's no frictional losses, we can set these energies equal to each other in our problems as we do problems in the chapter. The last thing I want to talk about is power. The power is the rate at which you do work. Of course, if you do the work in a shorter period of time, if you do the rate in a shorter period of time, the power will increase. You're delivering more work in a shorter period of time, more energy per unit of time. And the formula is power is energy over time. Now, most of the times you see it in the form energy as power times time. Most of the time you use it in your problem solving on the AP exam and sometime on questions is energy as power times time. So get used to seeing it in that form. Now, energy is charge times voltage. Okay, that's something we'll learn later down the road. So if you do some derivation, since power is energy over time, you've got charge times voltage divided by time is power. And we just said on the previous slide that charge over time is current, so power is also current times voltage. Now, the reason I show you these derivations are a lot of times you'll be asked to derive some of these things on the AP exam. So the more ways you see things derived, the better. The formula that you'll get on the AP exam is this formula here and this formula here, these two that I've starred. These other two forms of the formula I don't think are on the formula card, these two right here at the bottom that I'm circling. But let's see where they come from. Well, if P equals IV and V equals IR, that's our Ohm's law formula. If we plug in for VIR, we get power equals I times R, which is power I squared R. And then this formula here, we can get power equals current times voltage. And if I take and solve this formula, I get I is V over R. And if I plug that into here, I get power equals V over R times V, which is delta V squared R. And so that's what you get down here.